Hello there. So this is section 6.3, video number 3. So I wanted to make one quick note, present one quick theorem, and then just do a few practice problems, specifically kind of more theory problems. So the note is that in the orthogonal decomposition theorem, I might not have mentioned this, well, I don't think I've mentioned this yet, actually. The orthogonal decomposition theorem, if you look at the statement, actually allows the vector y to potentially be in the subspace W. So the reason being is if y is in W, then notice the way we've defined y hat actually lines up with, and I think it's theorem 5, the way theorem 5 tells us that an orthogonal basis should be linearly combined to give us y. That is, that if you look at how to express y as a linear combination of these basis vectors, it's exactly this, meaning that y hat is equal to y, which matches the intuition that y hat should be the closest vector in W to y, because if y is in W, then the closest vector in W should be itself. And on top of that, this would mean that the vector z should just equal the 0 vector. That is that basically there is no distance between y and W. So if you look at a previous theorem, I want to again say, actually I guess I can just check, I've got all the notes here. Yes, so it is theorem 5 in section 6.2. That theorem sort of confirms that if y was already contained in W, this is just the linear combination of these basis vectors u1 through up needed to get y, which means that we're just defining y hat to be y if y is contained in W. So just sort of write that down as a note somewhere, that this theorem actually does allow for the vector y to be in W, and then ends up sort of following along with our intuition. Other than that, I wanted to quickly state this theorem. So theorem 10 tells us that if we have an orthonormal basis for a subspace W, and remember an orthonormal basis is an orthogonal basis of unit vectors, and then the projection of y onto W is defined like so. And notice that this actually matches this definition, which is, again, this is the projection of y onto W, but we've just cleared the denominators of each of these fraction terms. The reason being because u1.u1, well, if all of these vectors are unit vectors, would just be 1, u2.u2 would be 1, and so on and so forth. Interestingly, and you can show this sort of just by expanding this matrix, so I don't want to go into it too much. If we let U be the following matrix whose columns are these orthonormal vectors, you can actually show that the projection of y onto W is actually just equal to U times transpose, times U transpose times Y. With this theorem, even your book kind of admits that like it's not the most useful theorem practically. If you remember normalizing a set of vectors or a single vector, you often do get fractions and square roots, and you know, even being a math person, I don't like fractions and square roots. And so generally, like especially if you're doing computations by hand, which you know certainly in a lot of classes you're going to be doing so, you tend to not want to use this theorem. Although certainly for like computational or applications where you're using a computer to assist you, or for theoretical purposes, this theorem might be useful. But it's worth stating anyways. So actually all I have left in this video is a few theory problems. So these are in the worksheet in the end of section 6.3. There's 4 of them, and I guess since we have some time, maybe I'll try going through all 4. So maybe I'll put 2 of them on the board, and then I'll let you think about them, and then I can discuss them. And so for all of these, we want to show that each statement is either always, sometimes, or never true. All right, so I think the first one is the most interesting of this set, although I actually have already proven one somewhere in a past lecture, very recently actually. So one is always true. The reason being is that if x is in W perp and W, then, so I should say if x is in W perp and x is in W, the relation we want here is that the dot product of x with itself is equal to 0. Why is that? Well, remember, if x is in W, well, first off, actually, if x is in W perp, right, that means that x is orthogonal to every single vector in W. But if x is in W, that means that x is orthogonal to itself. But remember, the only vector that is orthogonal to itself is the 0 vector, which implies that x itself is the 0 vector. So this one is always true. Number 2 is actually never true. The reason being is that we actually showed, I think it's maybe even a previous theorem, I want to say. Oh yeah, I've got all the notes right here. I can just check to see if this was in fact a previous theorem. Where we showed this. Yes, theorem 4. If S is a, well, actually, So theorem 4 is interesting because, well, so this one is interesting because I'm actually going to cross out my original answer of never true and put sometimes true. And so I'll explain why if S contains the 0 vector. So notice in this statement I had accidentally forgotten one specific thing, right? If S contains the 0 vector, then by definition S is linearly dependent, and S would be orthogonal because the 0 vector is orthogonal to everything. However, if I'd originally wanted this to be never true, what I would have had to change to make this never true is add the word non-zero. Then this would, you could use theorem 4 from section 6.2. However, if I don't add the stipulation non-zero, which I technically didn't, which I think this actually makes this more interesting, the answer would be sometimes, because again, if S contains the 0 vector, then S is automatically linearly dependent. So much fun. Gotta love math. So, a couple more of these, and then we will be done with this section. All right. So I'll put the last 2 on the board, and then I'll talk about those. All right. So, number one, this one is always true just by definition. So this one I chose because I wanted to sort of recollect the definition of an orthogonal matrix. So remember, an orthogonal matrix is an n by n matrix with orthonormal columns. And so actually that statement right there proves that the columns of U would form an orthonormal basis for Rn. This one, kind of funny, I chose it because I wanted a sometimes true question to be on there, unknowing that I had accidentally put a sometimes true question on there. And so I've already given away the answer for this one now. This is sometimes true. The reason being is if Z is in W perp, then Z should also be orthogonal to U2. So what this statement says is that if Z is orthogonal to U1 and W is this set spanned by U1 and U2, then Z is in W perp. And the answer would be sometimes true, right? In order for this to be always true, we would need to know that Z was orthogonal to U2. Right, and depending on that, it may or may not be in this set W, or orthogonal to this set W. So that actually wraps up section 6.3. We will move into one of the most important sections of Math 207, I guess next time, the Graham-Schmidt process.